Morning, everybody. Just wait for people to come in. It's 11:10 now. I got 365 of you. Seems to be our starting number these days. Hope everyone's doing well. It's as I was saying, it's kind of a rainy day in Toronto, but it's at least kind of warm. It was a nice day for a bike ride. I'm going to share my screen right now. And talk about, so on the agenda today is we're continuing along with chapter 6 on linear momentum. And so in this case, we're going to talk about impulse today and the impulse momentum principle. I'm going to do an example I wanted to do last time. We're going to go through that. I wanted to start out actually with some quick polls. So I was going to do these warm-up polls. First one is two carts collide, and we can actually do this maybe after the polls. One of which was initially moving and the other was initially at rest. Is it possible for both carts to be at rest after the collision? And here we are assuming that there's no external unbalanced forces acting on the cart. Yeah, so it's just A, yes, B, no. It's like a warm-up, a wake-up kind of thing. All right, and you can see there's going to be 2 more questions after this. Okay. Let's gotta show my chat. You don't have to make assumptions about the mass, I don't think. I'm going to disable the chat as I usually do. So if you chat, you can chat to me, just not to the whole class. Sorry about that. Where's my panelist screen? There it goes. So let's stop polling. So, whoa, this is a pretty close one. 60% said no. 40% said yes. So what I think, if you've got 2 carts, one of which was initially moving and the other was initially at rest, if you do the system, is both carts, okay, the P initial for the system is not 0, okay, because it's moving. Okay, so it is not possible for both carts to be at rest after the collision. So P final must be not 0 as well. Okay, you need external unbalanced forces, which is going to be called actually an external impulse, if you're going to want to change the momentum of a system. So 60%, not too bad. Let's do another quick poll here. This one's saying 2 carts collide, both of which were initially moving. Is it possible, can you imagine any scenario in which both carts could be at rest after the collision? Just give you 30 seconds to click on that one. So just 5 seconds. We'll share the results. So this one's 84% are saying yes, and I agree with that. I think we actually did that last time. It was the Velcro one, right? Which is, whoops, it's possible. So if both carts have equal magnitude, but opposite direction, momenta. So if you somehow set it up so the velocities and masses are such that they have equal and opposite momenta, then when they collide, they might stick together. So it's possible, especially if there's Velcro, if they are sticky. So there's different kinds of collisions. They might actually bounce off of each other if they're bouncy, but if they're sticky, then they could stick together and you could still conserve momentum. So if they have equal magnitude, opposite momentum, then P initial equals 0 of the system. And so P final could be 0. And P final could be 0 in a lot of ways. They could bounce off each other and still have 0 momentum, or they could stick together and both stop. So that was good. And then last question. Two carts collide, one of which was initially moving and the other was initially at rest. Is it possible for one of these carts to be at rest after the collision? Okay. Just give you a chance to click in. 5 seconds. These are just quick little quizzes just to get us, like I say, warm up. Okay, this one's 92% are saying yes. So yeah, that was something that I actually showed in the last time, is that it's possible for the momentum of that moving cart to transfer all of its momentum to the second cart. And so I can try to again show, just for fun, some of the different scenarios here. Let's point it down here. So, everybody, so again, sorry about the microphone. I'm going to turn it off in a second. But here we have two carts. The first one is if one of the carts is in motion and the other one is stopped, is it possible for both of them to be stopped? There's really no way to do it, right? Even if they're bouncy. So there's two configurations. There's bouncy and then there's sticky. So this is actually the third one. If you have equal mass carts and they collide, you can have one of them be stationary. There's also another way you can do this. It's called the trivial solution, which is you can have them not collide. So again, so the collision in this case, they miss each other. The collision is that they don't collide, right? So that's called the trivial solution, in which case momentum is conserved. Momentum just before they don't collide, and just after they both don't collide, it's the same. Or if they do collide and it's perfectly bouncy, then you can have one stop. The other thing we did is we said, can they both be moving but in opposite directions and stop? And they can. Okay. And if they were bouncy, and you did that, not sticky but bouncy. Whoa, I derailed. Well, let's try again. Then they just reverse their direction. So they continue with 0 momentum, but they've passed through each other. And they've reflected off each other. They can also pass through each other if they miss. Again, trivial solution. But it's 0 momentum in both cases. If you make one of these more massive, then you can move them at the same velocity, but the momentum is in this direction because this one overpowers it now because it's got more mass. Sometimes happens as well. Okay. So that's the demo. Let's turn on the mic here. Squeaky mic. But why, when they miss each other, is still considered as a collision? So I was just saying that, so what's going on here is momentum is constant when there's no external forces. So I guess it's not really a collision, but it's it's called the trivial solution because momentum is conserved even if they don't collide, I guess is the better way of saying it. So there's before, initial and final are going to be the same. Yeah, so why aren't both carts their own systems? So in this conservation of momentum, so if momentum is constant, then we are assuming there's no unbalanced forces on the system. So it's not true if you define that, you can define the system as one individual cart, but if they collide, if it collides with another cart, then certainly its momentum will not be constant, right? It's going to get changed because the other cart is outside the system. So what we choose to do is define the system as being both objects, in which case any collisions that they have, those are internal forces and they don't change the momentum of the system. So it's just a choice, right? Okay. And Ilian, you've had your hand up for a bit.
Hi. So my question was about the first poll question, where you said it was false, but I was curious, like if you had two very different masses, so you had one very, very large mass and one very, very small mass, and the very, very large mass was at rest, then when they collide, then like when the very, very small mass that is moving collides into the very, very large mass that is stationary, would they both be stationary? Like wouldn't they just like stop, if that makes sense?
Yeah, that's a good point. But I think mathematically they can't both be at rest. So, but you're right. I think if you had like the Earth and a little pebble, you know, came along, if the Earth was at rest and the pebble hit the Earth and stuck there because it was sticky, then they would effectively both be at rest at the end. So if you were thinking about that, then yeah, I guess that's a good point.
Okay, so then this would like, I guess this poll question would apply to like two similar masses.
I guess so, yeah.
Or,
I mean, mathematically,
okay.
there's always going to be some momentum.
Sorry?
So mathematically, there's always going to be some momentum, right? That's the that's conservation of momentum. And so, but you're right. I guess if one mass is very, very big, maybe it'll be negligible.
Oh, I see. Okay.
Okay.
Thank you.
Sure. And Yeaman?
Hello, Mr. Harlow.
Hi.
For example, last class, you said that when a single ball is in a free fall,
Yes.
There is a change in momentum, right?
Right.
And that means like in free fall, like generally there is a gravitational acceleration of 9.8, right?
Right.
And that means that when a system system is in an acceleration, there is an impulse.
Yeah. So the impulse in that case is coming from the force of gravity. So that's something that actually comes up if you look at the chapter 6 problems. There was one actually where someone was a stunt person that was falling and hitting on a cushion. And so I think he sank 4 meters into the cushion or something after falling 71 meters. And what they took into account there is not just the upward impulse of the cushion on the stunt diver, but also the downward impulse of the gravity during that same amount of time. So gravity exerts an impulse on a system whenever you've got something that's moving up or down. Okay, so that's yeah, a good point. Okay, I'm going to continue along. I wanted to talk a couple of quick announcements. So the midterm 2 was marked. Once again, the average was very high for this class, 75.5%. So you guys are doing fantastic. There's like 56% of you got A's on this. So that's good. I'm not sure exactly what all this stuff means during COVID. Like I say, I've never, ever had a midterm that wasn't in person with people at actual tables before. So these online midterms, I'm still getting used to them a little bit. Anyway, that's okay. I'm just happy that you're doing them and you're learning physics. That's the main thing, right? So have a look over the marking if you want. It's all, you should be able to click on it on your Quarkus now. I just unlocked it yesterday. I've posted, again, the detailed marking rubric called Midterm Assessment 2 Detailed Marking Rubric. For each problem, there was one TA that marked the entire class and took 32 hours to do that. This TA was consistent and stuck very strictly to my 2 + 2 + 2 + 2 rubric. Okay, you got 2 points for having completed each part, and those were taken separately. Okay, so if there was some mistake at the beginning and it carried through, you lost a lot of points probably because for each step was looked at individually. If it was the very last step and you missed something, then you won't have it, and the first 3 steps were perfectly correct, and you could get those 6 points. But part marks were deducted in the same way for every student in the class. If there is a mistake in your marking or in the computation of your mark, I would like to fix it. I will remark your test. All you got to do is send me an email to this Physics 131 fall, letting me know that there was a mistake and that you request a remark. And you have to do this by Monday, October 26th by 11:59 p.m. at the latest. After that, I'm not going to take remark requests. My TAs have already fulfilled their sort of union obligations of 32 hours each. They're not involved in the remark. They've made their decisions. They've gone through. They've told me very detailed of why students lost marks for what. So I'm going to be the one in charge of the remarks and correcting the mistakes. A few things to keep in mind. There's 857 tests and only one me, so please, please be kind. I will not be changing the marking rubric at this time because I don't think that's a good use of my time. There is a marking rubric. It's probably not perfect. Maybe it could be improved. Maybe I'll improve it for the 4th test or something. But my job right now is that I'm trying to get through these 11 chapters this semester, and that's where I want to spend the majority of my time. So if your answer was perfect, thorough, followed all those instructions exactly for the 2 + 2 + 2 + 2, you should get 8 out of 8 points. And that's what I want to make sure when I'm doing these remarks. But I'm not going to be overriding any partial credit decisions that these TAs made. As long as they were consistently applied to the entire class, then that is my definition of fair. Everyone was treated the same way. So I'm not going to change your mark. And I do reserve the right to reduce your mark if I notice a mistake that was in your favor. So 2 quick examples. Here's an example of a situation in which I would not increase your mark. Issue. For the first question, I received half a point off because my physical quantities and unknowns were not in the sketch and translate section. Instead, I put them in the represent mathematically section because this is the way I like to do it, okay? Result. And then the student actually says, oh, I did the same for question 2 and I received full marks. So that's a situation where certainly it's correct that you lose the half a mark for putting it in the wrong section in problem 1. If you did the same thing for problem 2, you should have lost half a mark twice. So I would reduce your mark by half a point there if you request a remark. You have to put them in the right sections as per the instructions. Here's another example. For the second question, I lost half a point because I reported the answer to 2 significant figures rather than 3. And I did this because I assumed that gravity is 9.8. So I've waffled a little on this one, but the final decision that the TAs made is that it was clear. I did say in the lectures that in this course, we're going to use 9.80 as being gravity. So I do require you, and since all the other numbers in that particular question, this is the grasshopper question, were given to 3 significant figures. I just wanted 3 significant digits in that thing. So it was applied the same way to everyone. Everyone lost a half point who did that, even though it's kind of correct if you use G 9.8. I believe your mistake was that it's 9.80. Okay. Feel free to send me an email. I'm happy to remark them, and I'll just make the time next week to do that. And then I'll say, I think this is the last announcement thing, is that I've been getting a lot of questions about homework number 5, which was on the Mastering Physics, which was a pretty long one, and the class average was pretty low. So I went through all 16 problems on the YouTube. There's a special YouTube video posted last lecture. And there's also like a track listing. If you want to just only see what I did for problem 5, you can just select and it'll jump ahead to where I start any problem 5 or any problem out of 16. It's kind of a long video to watch, but okay, everybody. Catherine, did you want to chime in?
Hi, this is a question about the midterm.
I can just barely hear you, Catherine. Could you go closer to your mic?
Can you hear me now?
A little bit, yeah.
If we have a question about one of the comments that they made on our midterm, and we'd like them to explain the comment, should we email you to get an explanation, or can we get in contact with the TA?
Yeah, that's a great question. So the answer is the TAs are done. You cannot contact the TAs. I guess you can try, but I'm giving them strict instructions not to. They've already gotten to their maximum amount of time that I've paid them for. So you can only just email me. And also, like I said, I don't think it's a good use of my time to explain the rubric again and again of what the TAs did this semester. So what I'm going to be doing is I'm going to remark, if you request a remark, because I do want to fix mistakes, but I'm not going to just spend hours and hours describing what the rubric was and what their decisions were. Okay. My goal here is I want to be fair. And if you, for some reason, made a mistake and you didn't get your right points, I want to fix that. So that's important. Tom, did you have a question?
Yes, so one sort of just general for the future for midterm 4, which is going to be handwritten. Is there any way we can remove the solve and evaluate step? Because what ends up happening is that when you do the represent mathematically, there are like a ton of variables. And is there any way we can just substitute at some point if we're trying to find time and substitute it in the represent mathematically section?
Okay. Yeah, I'm not clear that I completely understood, but I think that the idea is that I do want you to follow this 4-step method. It's certainly a huge theme of your textbook. If you're reading your textbook, like every page is going through this 4-step method and trying to, the purpose is, if you're kind of new to physics and this is your first physics course, having these 4 steps, these 4 general steps that you follow every time is very helpful in solving problems. You go through instead of like panicking and going, I don't know what the answer is, and being stuck, what you do is you just follow these particular instructions. You just go through step by step, sketch and translate. You know what that means, you lay it out. Simplifying diagram, you know what that means, you lay it all out. You're working through a problem given this particular framework. And if you're not new to physics and you're really great at physics and you did a whole bunch of physics in high school, then this might be a little cumbersome for you and maybe a little annoying for you. But I don't think it's your annoyance outweighs the kind of benefit that is gained from the students who are sort of more new to physics, who are really benefiting, I think, from having this kind of structure in the solving. So that's kind of my, and even if you look at Professor Seelfin and I, we had a lot of conversations about this over the summer of how kind of strict we were going to be on trying to teach this 4-step method, and we both kind of came down on this. There's a lot of research that's been shown that students learn better when you teach this this system. So that's what I'm going to try to do. Okay. Sorry, that's a little cumbersome. Certainly on the midterm that's coming up, it's just multiple choice, so you can sort of do whatever way you want. Let's do this example about the canoe that I was going to do last time, and I will actually show you how to do this 4-step method. So, okay. And actually, I'll talk a little bit about impulse in this. Laura, whose mass is, I'm going to call it M sub L, is 35 kilograms, is stranded without a paddle in a canoe. I'm going to call it mass canoe is equal to 65 kilograms. Okay. In a still lake 5 meters from shore. Okay, she has 10 kilograms of rocks on board. So I'm going to say mass of the rocks is equal to 10 kilograms. Yeah, on my page. So if she throws these rocks away from the shore, what is the maximum speed she can give herself and the canoe towards the shore? So what I'm going to do, initial, in the sketch and translate, you draw the initial and final situation. So there's a canoe, there's Laura. There's Laura, and there's this bag of rocks, okay? And everything's at rest. I'm going to define all three is the system. So if you do your little dashed line, all three of them. Okay. Okay. And the V initial equals 0 for all of them. They're all just sitting there. And then what happens is that the final situation is that the rocks are flying off this way, okay, with V of the rock final, I'll call it X equals -10 meters per second. So I'm going to define plus to be this way, plus X. And then you've got Laura and the canoe, okay, which are probably going to be going this way. V of Laura and the canoe, final X is question mark. That's the one we don't know. And it's still, in this case, the system is both of these, or all three of these objects. And I've said that LC, MLC is equal to 35 kilograms plus 65 kilograms is equal to 100. And so what I'm going to do is I'm going to assume that there's no external unbalanced forces on the system. So what this means is that the drag force of the water on the canoe is negligible. Be okay out there? What I'm going to do here is try to draw one of these momentum bar chart diagrams. So the way they work is you've got initial plus the impulse, external impulse on the system equals the final. So what I've got here is the initial is going to be 0 of the two things, of the rock and the Laura and canoe, plus 0 is equal to the final, which is going to be the P of the rock final, and the X. If we just do all these kind of, let's do a green line to be the 0 point, oops, 0 point. I'm trying to draw one negative and one positive. So the P final of the rock is negative, and the P final of the Laura and the canoe is positive. So what that looks like now in mathematically is going to be that mass of the rock times the V rock initial X plus mass of Laura and the canoe plus velocity of Laura and the canoe times initial X plus this impulse is equal to the mass of the rock times V of the rock final X plus the mass of Laura and the canoe times V of Laura and the canoe final X. And so this is 0 plus 0 plus 0 equals this, mass of the rock times V of the rock final X plus mass of Laura and the canoe times V Laura and the canoe final X. So, and we solve this out for V Laura and the canoe final X. V Laura and the canoe final X equals negative mass of the rock divided by mass of Laura and the canoe times the velocity of the rock final in the X direction. And so you got V Laura canoe final X equals -10 kilograms divided by 100 kilograms times -10 meters per second. And what I got is +1 meters per second. So Laura canoe final X. So this is toward the shore and much less than rock speed, which makes sense. And the question was, why was X defined upward? So yeah, that's a good question. So when you do these, let's go back one slide, because Annie asked a really good question. Why did I draw plus X upwards? So plus X is actually towards the right, but when you draw these momentum bar charts, I'm going to talk about that a little bit later today, you always draw your plus variable being up, so that the positive ones are up bar charts and the negative ones are down bar charts. Good question. Okay. Yeah, the JX I'm going to get to in a second. So let's go through some more stuff. What time is it here? Oh God, 11:40. Okay. In the canoe example, and also my lights went off. The idea here is that we were able to determine the velocity of the canoe and Laura by using the principle of momentum constancy. We did not need any information about the forces involved. This is a very powerful result because the forces that Laura exerted on the rocks as she was throwing them probably weren't even constant. They were probably pretty complicated, right? And all those kinematics equations that we used from chapter 2 are based on constant acceleration, so that you would need constant forces. So you're not restricted to just constant forces in these cases. So you can solve more kinds of problems. So the momentum of an isolated system is constant. So there's that sort of equation. If you have two particles, one and two objects, then the initial momentum, I called this sort of P initial, equals P final. But then you split it up into the two objects. And then sometimes what you see there, again, if it's isolated, meaning no external impulse, you can split this into two component equations, all the X components and all the Y components. So let's do a poll. A basketball with a mass of 0.1 kilograms is traveling down and to the right with V initial, X is +5, and V Y initial is -5. So that's sort of, it's going on a 45-degree angle, just before it collides with the ground. Then after it collides with the ground, it's got V final is +5 meters per second, and V, that's in the X, and V final Y is +4 meters per second. What is the change in the X component of the momentum? And I've given you a little list there. Let's see what you guys think. Is it A plus 0.5 kilograms? So this is the change in momentum in the X direction of the ball. Okay. And this is going to be, it's going to turn out to be the impulse from the ground. A couple seconds. Maybe 5 seconds actually to click in, please. Okay, good job. Yeah, so 78% of you who voted were saying E. So I like that. So basic idea here is that P initial in the X direction is this mass 0.1 times +5 meters per second. Okay, and P final in the X direction is also 0.1 times +5. And so the difference there, delta P in the X direction, is P final minus P initial, okay, which is 0. And let's do the next question, which it looks almost exactly like the previous one. Do you see the difference? Now I'm asking you, what is the change in the y component of the momentum? As usual, what we're doing is we're treating the x and y equations totally separately here. That's when you have to actually calculate it. Okay. Another 10 seconds. Click it in. Thank you, thank you. Let's see what share results are saying. A lot of you are saying D plus 0.9. I think that's right. Let me just see if I got it. So P initial Y is equal to, it's going to be 0.1 times negative 5 is going to be negative 0.5 kilograms meters per second. Those Harlow's, whatever. P final Y is equal to 0.1 times plus 4 meters per second is plus 0.4 kilograms meters per second. Delta P is equal to P final Y minus P initial Y, right? So it's going to be plus 0.4 minus 0.5. So it's going to be plus 0.9 kilograms meters per second. So I like D. Very good. Okay. Impulse. So this is this J. Okay. The impulse on a particle is given by two equations. The x component of the impulse is the, I guess, the time integral of the x force dt. And the yj is the time integral of the y component of the force. So impulse has units of newtons times seconds, but you should be able to show that newtons times seconds is equivalent to kilograms meters per second. The impulse momentum theorem says that the change in a particle's momentum in either the x or the y direction is equal to this impulse. So impulse, this is like an area under the curve. We're not going to be doing any integrals in this course, but that's what this thing, that's an integral sign. But basically, if this is the average force times delta t equals this area, which equals this integral of f dt. Okay, so we're going to use this. We use this. The F average times delta t is your impulse in the x or the y. That's impulse. So example, you've got a ball which before it hits the wall is traveling with a positive velocity, and then after it hits the wall, it bounces off and is going with a negative velocity. So this is the impulse of the wall upon the ball. Okay. So this is the force, I guess, of the wall on the ball. And what happens is there is some area under here. This is the impulse of x of the wall on the ball is less than 0. It's a negative area. So it changes the momentum to from being initially positive to being finally negative. So this force times delta t, it has a consequence that if you stretch out the length of time, you can change the same amount of momentum with a smaller force. Or if you reduce the amount of time of the force, then you have to increase that force. So this is why we have airbags. If you consider a car accident in which you're in a car, you're initially traveling along at 50 kilometers per hour, and then you hit a bridge, the car comes to an abrupt stop. So it's better to hit the airbag than it is to just hit the dashboard. So the person inside must reduce their momentum from being going at 50 kilometers an hour down to 0. And they have a certain mass. So that's a fixed amount of delta P. So they can do that with a force applied over a short amount of time when they hit the dashboard, or over a longer amount of time if they squish into this airbag. If the person hits the airbag, it squishes during the impact, lengthening this delta T of the time to stop. So this takes longer, so the average force is less to give you the same change in momentum. So that's kind of cool. Let's do another quick poll here as we're doing it. A 100-gram rubber ball and a 100-gram damp cloth are dropped on the floor from the same initial height. They're both traveling at the same speed just before they hit the floor. The rubber ball bounces, but the damp cloth just goes splat and hits the floor. Which object receives a larger upward impulse from the floor? Is it going to be A, they both receive equal impulses, B, the damp cloth receives a larger impulse, or C, the rubber ball receives a larger impulse? We're not going to do any actual integration in this course. It's an algebra-based course, but I wanted to show those areas just in case you know about it. No calculus. I promise. And there's a lot of questions about which chapters are on midterm 3, so it's chapters 5 and 6, right? The ones we're doing right now. Which is on the, if you look at the list where all the YouTube links are, you can see which chapters are in which test. You guys ready? 3, 2, 1. Ooh. This is the kind of one where I would hope that if we were, if you're actually in a classroom, you'd actually discuss this about this. So either they receive equal impulses, 40% of you said that, or C, the rubber ball receives a larger impulse. So I actually thought that it would be the rubber ball. Why did I think that? So I've written it out here. So they both have, I guess, let's see here. If you define, I guess, define plus equals down, which is what I've done here, then what happens is that P initial is positive. Okay, so if P final is 0, then delta P is going to be this negative P sub I for the damp cloth if it stops. But for the rubber ball, it goes back up again with a negative momentum. So their delta P is negative PI minus PI, you're going to get -2. So this magnitude is greater. So the magnitude of delta P for the ball is twice as much. It takes twice as much impulse from the floor to make something bounce than it does to just make it stop. Because you're changing, to make it bounce, you have to stop it and you have to, again, push it back up again. Okay. So I want to talk a little bit about these momentum bar charts. I got about 5 more minutes left here. So this is from section 6.4, the generalized impulse momentum theorem, which is that the initial momentum plus the external impulse equals the final momentum. So it's just like conservation of momentum, which is when initial momentum equals final momentum, but now we've added this new thing, which is the external impulse. And it looks, this is the crazy equation she puts for equation 6.9, but basically, you know, this is this, you got your initial momentum, so you add up the m times v's of all the particles. this thingy is this area, right? This J. Okay. And then this right here is the final momentum, just the final m times v's of all these particles. Okay. So, and if the external impulse is 0, then you've got conservation of momentum. Momentum is constant value from initial to final. So this is this idea of how you draw this. So example, you've got two carts that were initially moving towards one another. The momentum of cart 1 is greater, I think, than the momentum of cart 2. So they eventually stick together, and then they're traveling along in the same direction that cart 1 was originally. So we put X to be to the right in our sketch of the situation. But when we diagram out the momentum bar charts, we put X being upwards. So we first sketch the system, initial and final. Choose the system, which is both carts. Then you draw the initial and final momentum bar charts for each object. So initially, 1 had a positive momentum, and then 2 had a negative momentum, but it wasn't as much. Okay, so it was negative, but it's going slower. So you put a smaller bar chart there. There's no external forces, so our J here is 0, equals 0. And then they're moving together towards the right, so they both have some positive and smaller. And the idea here is that since the area was originally 1, 2, 3, minus 1 is 2, then the area of these should be 2 as well. So the area of the bar charts to the left of the equal sign equal the area of the bar charts to the right of the equal sign. So that's our sort of conservation of momentum idea, is represented by these bar charts kind of summing to be the same on the left and the right of this equal sign. So 1 is you sketch the process, choose the initial and final states, choose a system. 2 is you draw initial and final momentum bars for each object in the system. 3, you draw an impulse bar if there is an external non-zero impulse. And 4, you convert each bar in the chart into a term in the component form in that equation. So when you're setting up represent mathematically, you write the MVs for all the momentums, and you write the F delta T's for the impulse. The lengths of the bars are qualitative indicators of the relative magnitudes. The middle shaded column, that J, represents the net external impulse. The sum of the heights of the bars on the left of the equal sign equal the sum of the heights of bars on the right. This is this sort of conservation of bar heights represents the conservation of momentum. So that's sort of how we do that. Getting a little late. I was going to do an example, but I think I'm going to skip that one. Due to time. I'm going to do it next time. I'll do it on Friday, on Crazy Friday. Just see how we're doing here on the, oops. Guess I'll go to here. Okay. So once again, on Tuesday, so like a week from yesterday, there's going to be midterm number 3. This will be a multiple choice one, very similar to midterm number 1. So the odd numbered midterms are the same, which is that there are 10 multiple choice questions, and you have to answer them in half an hour, and you get the questions delivered one at a time. It's all multiple choice. So between now and Friday, I want you to finish up reading chapter 6. That'll bring us to the end of the material that's going to be covered on the midterm number 3. Also, please plan to meet up with your practical pod mates on Friday. We're going to have another one of these team up quizzes. This will be based on chapter 6 stuff. Also, during the class, I'm going to fire up the Physics 131 Help Center. So if you just go there instead, if you know your practical partners aren't going to make it, you can meet new friends in the Help Center on a separate Zoom call, I guess. And then I'll set you up into breakout rooms for that, so you can chat. I'm going to stick around here for the next half an hour, and then we're going to switch it over at some point over to the help center. So thanks very much. And I'm going to turn off the record now and go to some questions.